started this work at UCLA when we were both out at IPAM and finished it up a little while ago. The paper is on the archive if one needs more details, so we'll see how it goes here. Okay, so this was motivated by a number of recent work, and Felix Otto began to develop the idea that one could look at a number of evolution equations for probability measures as gradient flow on the space of probability measures with respect to a metric, the 2 Wasserstein metric. And the advantage of this is when you use a different metric for the gradient flow, you have a different class of geodesics, and since you have a different class of geodesics, different functionals become convex. So in other words, one can write the heat equation as gradient flow for a variety of metrics and a variety of functionals. And it was a simple case. Of course, not many questions one has about the heat equation these days. But the simple case of this is that the heat equation is gradient flow for the entropy integral rho log rho with respect to the 2 Wasserstein metric. It's also, with respect to the L2 metric, a usual norm metric, it's gradient flow for a certain energy integral. Okay. The advantage of this.
So you will explain what the 2 Wasserstein.
Right. So I'm going to explain what this metric is, and it's a non-norm metric. It doesn't come from a norm. There's a price to pay for this, but the advantage in these applications is that one gets additional convexity. Because of the additional convexity, things happen at rates that one can estimate using the convexity, and people like Otto and then Barta proved a number of sharp functional inequalities using these ideas. And Felix Otto got the first sharp rates on estimates on the rate at which solutions of the fast diffusion equation approach their equilibrium, these so-called Barenblatt solutions. So this is what we'd like to go to. Now, here's the 2 Wasserstein metric in a way you may have seen it first. And so one looks at the set of all couplings of 2 probability densities, rho naught and rho 1. These are probability densities that have finite second moments, so that this thing will make sense down here. And to say that they're a coupling means that the first marginal is rho naught and the second marginal is rho 1. So if you integrate them against the test function that just depends on one variable, that happens. Okay? On the simplest coupling, there's always one coupling, which is the direct tensor product of the 2 densities, but there can be all kinds of others. Okay? So the 2 Wasserstein distance, the square of it, is the infimum over all couplings of this quantity right over here. Okay? Now what this has to do with transport is the following thing. At least in the classical case, we can take the conditional probability, take this kxy, and divide by the density rho naught, and this gives us a transportation plan. That is, it gives you a Markov transition function, and you can think of it as specifying how the mass at x is to be distributed over the possible sites y it can go to. So this is a transportation plan, and then you're looking at the total cost of all of these different transportation plans when the cost of transporting unit mass from x to y is that. Okay? So that's what this is. Now, when you get to there's a lot of words up there. When you get into quantum mechanics, we replace these probability densities with density matrices. Okay? And there's a quantum version of probability theory that was promoted by Irving Siegel. If you think of the space of bounded measurable functions in some probability space equipped with convex complex conjugation as the involution, it's a commutative von Neumann algebra. Now, if you just drop the requirement for, and it has a state on it, the state being the probability measure, that is a positive linear functional. You take a positive operator, which is a positive function, you integrate it, that's a positive linear functional. If you drop the requirement that the algebra be commutative, then you have a non-commutative probability theory. And the reason this is of interest in applications in mathematical physics, or Siegel was promoting, is that certain operators, for instance, fermion creation annihilation operators and Hamiltonians have a simple representation in terms of operators from certain non-commutative von Neumann algebras. So the simplest representation of the operators is operators on a non-commutative LP space. Okay? Now, if we go into this non-commutative setting, it's difficult to see how mass transportation might work out right away. And the big problem here is that in a non-commutative setting, there's no analog of conditioning. So there are all kinds of problems that I've struggled with, and many of them I still don't know how to solve, that come from in classical mechanics. You know what conditioning means, and there's no good analog of conditioning in this quantum probability setting. So it's not clear what a transportation plan might mean. Now, couplings you can still write down, because you can write down a density matrix on the tensor product of the Hilbert spaces that has two given marginals, and we could call that a coupling. And at least in the context of free probability, Bien and Voiculescu came up with some sort of analog of the cost function. But one needs some extra structure, because in general there's no analog of this Euclidean cost function over here. Okay.
Does Voiculescu use this notion of cost and so forth?
They have it right. And there's a notion of cost that's appropriate to the free probability. But and then it's directly in terms of the marginal construction. So you can integrate against some observable which plays the role of the cost. Okay? So we'll have another analog of that coming up here, but one needs some additional structure to make sense of it, because there's no underlying metric space and no distance from x. I mean, there aren't any points. This is again the problem with the no conditioning. Okay, so there are interesting evolution equations, however, that on the classical side, for instance, the Fokker-Planck equation or Ornstein-Uhlenbeck process, these equations have a very close connection with the gradient flow in the two Wasserstein metric. And you can prove a lot of functional inequalities from this point of view. And these things have quantum mechanical analogs. There's a fermionic version of the Fokker-Planck equation. And some number of years ago with Elliott-Lieb, we proved a sharp logarithmic Sobolev inequality for this in this fermionic setting and optimal hypercontractivity. And now one can look at these things on the classical side profitably from a mass transportation point of view. And this might suggest that there should be a way to do this in the quantum mechanical setting. And to a pretty good extent one can, and that's what I'd like to explain here.
So you have defined this, you haven't defined the Wasserstein, right?
Right. I haven't defined it yet.
Because you just use the L2.
Mm-hmm.
We don't know what it means.
We don't know what that means here. And so there's another way to look at it, and this gets close to what we'd do. Here's another formulation for it. And we want to study evolution equations anyway. Okay, but here's a sort of a continuous time way of looking at it. If we can write any, so if I have a smooth path in the space of probability measures, I can always write it in this way in terms of a continuity equation. Right? Because, okay, there's more or less a formula for this. Since these all integrate to 1, this integrates to 0, so I can take the inverse Laplacian of this thing, and that's a divergence of something, and so forth. You can always do that. In fact, lots of ways. Okay, so I can always write any d rho by dt in terms of some vector field. Okay?
Vector field will depend upon it.
Right, from the rho. In fact, one way, the cheapest way to get such a thing would be to start with this guy and take the inverse Laplacian of it. Okay, these things will be easier in the fermions. I'm sweeping over technical things that might worry you on Rn, but don't worry about them. We'll deal with them rigorously in the fermionic case, but it's okay here too.
You're saying there is a V, but it's not unique.
Well, it's not unique, right? But there is some uniqueness associated to it, and this will come up shortly. But here's what another version of a coupling. So we'll use the same symbol for it. A pair rho v with this vector field couples rho naught and rho 1, provided the continuity equation is satisfied, and you start out at rho naught and you go to rho 1. So this is just a path in probability connecting these guys up.
So I see that you have 60 slides. And it's a sort of slow
Many of them.
guide, so I cannot take notes. Is it possible that these slides will be made available?
Sure, I think it's being videotaped, the paper's there. Many of the future slides have very little stuff on them, okay? I don't do this thing where the slides go dot, 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 new stuff appears on them. These are all just one-shot slides, so don't worry. Don't worry, okay? But the slides are available. I'll send the slides and the papers on the archive and so forth. And so here it is. Okay, so anyway, here's this thing, and you'll recognize, I mean, this should look familiar for computing a distance squared if you're doing a Riemannian distance with a metric over here, and you take the derivative length of the derivative squared, and then take the infimum of the action over all paths starting at one point and getting to the other. This gives you the distance. And indeed, this formula was implicit in Otto's formal theory of the two Wasserstein distance as induced by a Riemannian metric. So what's not obvious from the previous formula I wrote down at all is that indeed this distance is a Riemannian distance.
Oh, it's a Riemannian.
It's induced by a Riemannian metric. Right? Right. And so here's where this gets into the next question you're asking. If you look at all the vector fields W, infinitely many, for which the continuity equation is satisfied at some fixed time t, well, this is a convex closed set, and so it contains a unique element of minimal norm in this L2 row space. And so that has to be orthogonal to all vector fields such that the divergence of this is 0, because those are the perturbations you add. But that means you're orthogonal in L2, just plain L2, not L2 row, absorb the row in now. You're orthogonal to all divergence-free vector fields, and hence it's a gradient. Okay? And so there's a minimal thing that you put in here among all these vector fields. There is one that's a gradient, and that's the one you could restrict to anyway, because that's going to at least minimize each of these integrals at that time t. Of something, of some potential, right. Mm-hmm. And then there's a theorem of Brenier and McCann, which tells you that the structure of this optimal coupling, that it sits on the gradient of a convex function, and you can tie these two things together through that. This is a different story, but that's how you identify this W2 distance with the other one. So you know the structure of the minimizers.
So they're the same.
They're the same, and so this is another way of looking at it, okay, in terms of this. Now, this gets a little closer then to what we'd like to look at, okay? Right. Okay, and so indeed, then this suggests also what the Riemannian metric is going to have to be, and this is what Otto wrote down. You identify the tangent space. I mean, what is a tangent vector? It's an equivalence class of curves, so you take all these curves that have the same derivative, we can identify them with this u, this vector field gradient u, and then we can identify the length squared of u as the integral against rho, and that's exactly what the metric would have to be to make this formula back here do the usual thing. Okay, well, replace this now. You may as well put in the gradient of u here, and you can think of the gradient of u as the tangent vector at rho naught, because the d rho by dt, here it is, the d rho by dt, there's a unique gradient u in here, and so that specifies the time derivative of the path. Okay, now what's the length of that thing? If we're going to tie it in with the metric, if I make this the Riemannian distance squared, length squared of the tangent vector, then this becomes the usual action formula for the Riemannian distance in the manifold. And so somewhere between Brenier and Benamou and Otto, who were doing these things at the same time, Otto had this formal Riemannian structure, and Brenier and Benamou were rigorously deriving this formula for the Wasserstein distance. That's what the metric has to be and is.
So I mean, this is the usual thing. You claim every curve in the space of densities is generated by a gradient vector.
Exactly.
Mm-hmm. Therefore, the gradient vector fields are tangent vectors.
Right.
Mm-hmm. Kind of manifold of densities.
Mm-hmm. And then you put this length on them, which has the rho built in. If you left this thing out, you'd get an h-1 norm, effectively, for the distances.
This is not 19th century. This was only done a few years ago. It's a little surprising.
Well, it's quite surprising that this was done. I mean, these non-norm metrics and applying them to PDE is a very recent thing. What's perhaps even more surprising is that the Brenier-McCann theorem about what are the nature of the optimizers for this first thing I wrote down, I mean, in terms of the usual couplings, this was only done in the 1990s, and the Monge problem goes back to the late 1700s. But it had the distance, not the distance squared. So you would think that sort of a natural thing to do somewhere along the line would have been to replace Euclidean distance by Euclidean distance squared.
Distance squared is easier, isn't it?
Much easier. Much easier. In fact, there's a long story. So the other one is quite hard. And in fact, there were mistakes in an important key theorem of Sudakov's completing the solution for the one distance problem that didn't get patched up until after the L2 case was worked out. People didn't even notice it was wrong at first. Okay, so anyway, so there's what that thing is. So this is this. Now, there's a close entropy between, a connection between entropy, the Wasserstein, and Fokker-Planck, and so this will probably be quite familiar, but let's just explain it. So here's the very simple equation, linear equation. This is the Fokker-Planck equation. Here's the standard Gaussian measure, and I can write the density. This is the Fokker-Planck equation written for a density with respect to Lebesgue measure, and much of what we do to make a contact with what we do with density matrices later on, it will be better to think of it as a density with respect to this Gaussian measure. So if you make this change of variables here, which is all that is, then this thing just, that's what the Fokker-Planck equation becomes. So we'll call this the Fokker-Planck equation. Here's a nice formula for it, the Mailer formula, where you're doing a rotation. Think of this as cosine theta, then this would be sine theta. So you're doing a rotation and taking a marginal, and that gives you a semigroup, and there's the complete solution of it. One knows everything about this equation. Okay? It's a positivity preserving Markovian thing, so if you differentiate, there's a Dirichlet form for it, just the generator integrating by parts, which is this gradient squared integrated against that. Okay, so this is that. And this operator that's associated to that quadratic form, that's the number operator. The eigenfunctions are Hermite polynomials, and the eigenfunctions are, eigenvalues are just the integers. Okay, so that's simple. Now, so that's, those go by pretty quickly, but this is familiar stuff. Okay. Now, given a probability density with respect to Lebesgue measure, the relative entropy with respect to gamma, which is this quantity down here, is this stuff. So it's got the f log f, but there's also this quadratic term in it, and that's the same quantity as this if you write it with respect to the Gaussian measure. Now let's differentiate. Okay.
What's the rho there?
Well, rho. So here's rho.
There it is. No,
So this is
oh, rho, yes. So that's the Riemannian derivative.
right. So it's preferable. If you think of it in terms of with Gauss measure as the reference measure, then this relative entropy is just this quantity rho log rho. Okay, and up here it's got this term in it. Okay, and this thing over here, right?
So, I mean, usually there is a sort of a log rho minus log gamma, but maybe, in a entropy there is a difference of two Hamilton functions or Hamiltonians, but maybe one of them is 1, and so the log.
Right, you lose. Right, because if you, well, these is where these constants go. Because if you take the log of gamma, of course, it just comes out in terms of the second moments, and the second moments can be computed, and there they are. And here's the log of the x squared against the f, and so this is, I mean, this is it, right? So this is exactly what you say. If you take minus log of gamma, you get a second moment. Sorry, it's not what it, this is xf, and here's the normalizing term. So this is the usual. Right, it's exactly this thing, and you can cancel this guy off with this, and then exactly as Jörg is saying, what's left over is integral f log f minus f log gamma, and minus f log gamma works out to be this. And this, you just do the integral because it's a constant. Okay? Now, when you, okay, so let's skip that. Let's just go on to the thing over here. So if we take this Fokker-Planck equation, we can write it as a continuity equation, like so and so, and here's the v which does it. So if you take this v, you get the continuity equation, obviously, because you take the gradient of this, you get a grad f over f, but here's another f which goes back into it. And so this is the minimal vector field to put in because this is a gradient. There's a unique gradient which minimizes the length, and so that's what it is. So this is the tangent vector field to the curve because it's a gradient vector field, and that's the unique thing that minimizes the length. I'm about to differentiate the entropy along the flow.
This is our general situation. We're back to the general situation now, right? You were talking about.
No, this is the Fokker-Planck equation.
Yes.
Right. So this is the general thing. This is general.
Yeah.
But now take this choice for v.
Yes.
Okay, now what do you get? If you take this choice for v, see this is grad log f, so that's gradient f over f. But here's another f in here, so that gives you divergence gradient f, so that's a Laplacian f.
Yes.
And this gives you a divergence x dot f. Right, and that was the Fokker. Well, this tells you what the tangent vector field is. So if I take a solution of the Fokker-Planck equation, that's a curve in probability density space. It has a tangent vector. I want to think of that tangent vector as a vector field on RD. What is that vector field? Okay, well, it's the unique gradient vector field which makes this equation true, and so there's what that is. So this is the gadget which goes in here, and as we're saying this, there are many choices, other choices I could have put in here, because anything that makes the divergence drop out is okay too. It makes this okay, but this is the unique one that's a gradient, and it's the one that makes this the smallest, which is good for the variational thing. And so, therefore, from this Brenier-Benamou formula, if you look at the Wasserstein distance squared over a small increment along the flow from this Fokker-Planck equation, it's this quantity right over here, which again is telling you what this metric is. Okay, now let's differentiate the entropy. And here's what you get. If you differentiate the entropy, okay, so you get, this is just the usual thing. You integrate the logarithms. Here's the d rho by dt. You integrate by parts. And this, what you get on this side is again the v. And so that's the minus v squared. But that's just this increment in the Wasserstein distance. And so this is the basis of this connection, which suggests, it doesn't quite show it, but this was what proved, what led Kinderlehrer, Jordan, and Otto to suggest that, in fact, this Fokker-Planck equation should be gradient flow for the entropy. Because if it is gradient flow for the entropy, this is exactly what you get. The tangent vectors line up, so you get the length squared of the speed, if it's doing this. Okay? Now, then, once that's true, how do you exploit this? Well, then, if it turns out that this entropy function, this relative entropy, is a strictly convex function in terms of Wasserstein space, meaning if you take the geodesic between any 2 points and differentiate along it, the second derivative is bounded below. And the kind of surprising thing about it is if you look at this entropy, which we had it back over here, this term is convex, but it's not strictly convex. The Hessian is positive, but there's no, in infinite dimensional setting, there's no lower bound to the Hessian. It's this term which looks linear, or looks affine, that gives you the strict convexity. But on the Wasserstein space, this is not an affine function. If you take a geodesic, it's strictly convex. So this simple term is the source of the strict convexity of the relative entropy function. And this is what Otto and company exploit, proving in functional inequalities. There's a similar thing for the fast diffusion equation. And if you want to understand the contractivity property, it comes from that. Okay, so here's, so what this, so this is how these things are tied together. Okay, now, right, here is this. Okay, right. So when we want to do this now, go over to the fermionic setting, and we have to introduce a space. We're going to need some extra structure to work. We've got all this differential structure going on, and we've got logarithmic derivatives coming in this thing, and that's because we're dividing by an f of t. But anytime you start dividing by density matrices, remember conditioning is a tricky thing to do, quantum mechanically. You can't just divide by the density matrix because one density divided by another won't in general even be self-adjoint, let alone a conditional probability distribution. So it's not clear how to begin to write down even a continuity equation, what that would mean. And we're going to work backwards through dissipating the entropy because we know what the entropy is and we know what this evolution equation is. And by differentiating the entropy and staring back at this formula, which involves the distance, and relates it to the continuity equation, you can come up with what that should be.
So, Eric, did you tell us already what this, go back a slide, what this Fermionic Fokker-Planck equation looks like?
No, that's coming right up. Okay. So now again, anytime you want to make sense of, one needs some structure, and there's, in the setting of free probability, there's an approach by Bien and Voiculescu, which is an interesting mathematical structure, and I don't know if it has any applications in math physics or not, but anyway, that's not what they were after anyway. Here is this one, and I would work in this structure here. So this is, let me explain the von Neumann algebra we're going to work with, and it will set it up in a finite dimension, but independent, arbitrarily many degrees of freedom, and all the estimates will be independent of the number of degrees of freedom. So here are the canonical anti-commutation relations. So you have n operators on a Hilbert space, and they anti-commute like so. These are the generators. Okay? Now, here's a construction of them for those, if you haven't seen them. Take the Hilbert space on which they'll act will be C2 tensor C2 n times. So a 2n dimensional Hilbert space. And Qj is the product of the following thing. Okay? So the first j minus 1 factors in here are this u. This goes back to Jordan and Wigner, this construction. The jth guy is the q. Okay? And after that, you have the identity. So you put the q in the jth place, this is a Pauli matrix, and you put u's back in here, and because of the properties of the Pauli matrices, then some u's hit some other u's when you commute it, and this gives you a construction of these things. And maybe also Bauer and Weil did something like this a long time ago. So concretely, that's what this thing is. So that's an algebra. there's a injection of the Rn into the algebra. You take a vector x and just take x times the qj's, and you get an operator so that its square is length of the vector x squared times the identity, and this is often taken as the defining relation for this thing. Okay? Now, that's an algebra. Think of it as the analog of the ring of measurable functions. Here's the probability measure on it, or which is positive linear functional. So it's the normalized trace, which can also be written as a ground state expectation, if you like, but the simplest way to talk about it here is just the normalized trace. So take the trace of an operator in this algebra, usual trace, and divide by 2 to the n. Okay? And obviously, if you've got a positive operator, you get something positive. Okay? Now, this is going to look like this should be really easy to prove everything in this setting when we start talking about this right away, because these are the analogs of the Hermite polynomials. If you take a fermionic multi-index is just n tuple where each one of these guys is 0 or 1, and set magnitude alpha, vector alpha to be the sum of these entries, so the number of ones, and q alpha is this product written in this order. And it's easy to see from just writing out this in this explicit representation that the trace of all of these things are traceless except for, of course, the identity, which is what you get with the alpha equals 0. Okay? Now, even more, these things turn out to be orthogonal to each other. In fact, you can see right here, if you take two of these things and bring them together using the commutation relations, you can cancel out all the overlap, and you're left with something else, and so, which is then traceless. And so those are the Hermite polynomials. So the Hermite polynomials look really dead simple in this setting. So, okay, how can anything be, yeah?
Are you going through this Clifford? Couldn't you just say that you look at von Neumann 2, 1 is a trace, and they talk there?
Well, because, okay, this is the, probably if you just wanted the trace, that would be okay, but on the next slide coming up, I'm going to need a differential calculus. So the raising and lowering operator, but I'm sure you could do it in another language, and I'm going to follow Lenny Gross's notation because that's who I learned it from, I guess. But yeah, so you'll see when we do the differential operators. Okay, so this you should think of this tau. This is a point Irving Siegel emphasized a lot. This is a non-commutative analog of Gaussian space. So why is it Gaussian? Okay, well, a characteristic property of Gaussian is orthogonality implies independence. If you take two random variables that are supported by, that are functions of coordinates in orthogonal subspaces, and you take the expectation of the product is the product of the expectations. That the same thing happens here too. If you take two operators A and B, and they're generated in the sense we saw before by two orthogonal subspaces of Rn, then the product of the traces is the trace of the products, and that characterizes this measure on here. So this really is some kind of non-commutative analog of Gauss space. And so the other guys really are some kind of non-commutative analog of Hermite polynomials. And so you can think of this L2 of this space as it's the Fermionic Fokker space, but thinking of it as a Gaussian measure. Okay, now there's a differentiation operation. Let me watch what I'm doing. Okay, so there's a differentiation operation, and it's just this. Remember that since the qi squared is 1, if you multiply something on the left by qi, okay, if there is a qi in this guy, you can bring it out to the left. You're going to pay some signs for doing that, and when it comes out next to this guy, it goes away because qi squared is 1. If there's no qi, it's going to be 0. Okay, so this is a derivative operator, a lowering operator, if you like, and with some signs put on the left. Okay, and this is a gradient operator, so you just apply these things in each of the coordinates. There's a formula for it, and the formula involves this grading operator. Okay, so that is, if you can multiply this thing on the left by the q and on the right by the q, and if you put the grading operator, now the role of the grading operators, and you commute this guy through over here, if there wasn't a qi in the middle, things will just cancel out because you're going through.
Oh, so that's the definition. Yeah.
Right, it's the same. It's equivalent. This is another way of writing it. This is maybe a more standard way of writing it, where you can recognize these things as lowering operators. Okay, but it's also convenient to write it like this for what comes next. And you can see it's the same thing because if there is no qi in here, then when you commute this guy through, you change signs for the full count of times, and then these things just cancel out, so you get to 0. Otherwise, when you hit the qi, you just commute right on through, and there's one different sign, and it works out just right. Okay? So these things have a Leibniz rule, which you can see by that, and the Leibniz rule has this grading operator showing up in it. So this is, otherwise, you have something like the usual calculus. Okay, good. So there are a bunch of identities. Let's skip that. That's not going to be very enlightening. Okay? Now, the adjoint of this thing is a divergence. Okay? And that would be the raising operators, which are fine. So here's a formula for those. Okay? And, okay, once you've got the there's a divergence of a vector field, which means you apply these raising operators in each coordinate and sum the things up.
So you would not want to develop a more general notion of differential forms and exterior derivative. It's adjoint.
Well, you
It's the beginning.
It could be quite useful.
it could be, but I mean, this is sort of a bare bones, just enough to write down this generator, thinking of it as, I mean, something involving derivatives and gradients and divergence forms, so I can make sense of a continuity equation. So this is the minimum amount of structure. I guess we're talking about this guy in that form. Okay, so here we come to this thing. Let me write down this Dirichlet form. So here is this gadget. So you've got an observable A. You take its gradient, take the adjoint to the gradient, dot them into each other, and take the trace, the normalized trace. You can write this in terms of a vacuum expectation value, but this thing then defines the fermionic number operator. And again, the spectrum is just raising and lowering operators, because that's what the adjoint of the guy is over here. And so that's just the exact analog of this thing. So we call that,
The Dirichlet form is just a number operator.
it's the quadratic form associated to the number operator.
But you don't have any weight in the trace, so you don't.
Right, there's no weight, but you should think just, I mean, it's, so when we did the one for the classical case, we integrated against the Gaussian measure.
Right.
And as I was explaining before, you should think of this tau, even though it has no weight in it, looks very flat. You should really think of it as having the Gaussian measure put in, or at least this is what Irving Siegel would insist upon, saying this is the Gaussian measure because of this.
The analog of that.
And so it fits exactly. So to the extent that this is the Gaussian measure over here, and this is gradient squared, then this number operator is just really complete parallel. Okay? And so then there's this Mailer semigroup, and good. And so this is the Fermionic Fokker-Planck equation, which is just this thing. Okay? Now, again, the parallel runs pretty deep, and this is what part of what motivated this thing. If the number operator here is the boson operator, then not only is this a Markov semigroup and therefore a contraction in all LP, but it has this hypercontractivity property of Nelson, and so it maps LP into LQ for higher Qs, and as soon as e to the minus t is bigger than square root of p minus 1 over q minus 1, you get there, and that's sharp. And it turns out that that's also sharp for the fermionic case, because we have this trace, we have LP spaces. You take them, to apply tau to the absolute A to the P, right? You've got LP spaces. And this was a theorem proved by myself and Elliott Lieb that you get the exact same sharp hypercontractivity property. This was conjectured by Lenny Gross, and he proved it with almost the sharp constant. And then, well, we fixed it, we finished it up. And the proof is rather intricate. It relies on dimensional induction, and it relies on having an optimal estimate on how uniformly convex the unit balls in the Schotten norms are. So it uses a sharp estimate for 2 uniform convexity, and something that's rather far removed from what one does in the Gaussian case. Okay?
This is just for the number operator.
Just plain number operator, but this is so you can put weights. You can put weights in it too. I mean, but this is just so the fermionic thing. This is the fermionic analog of Nelson's the Nelson's result. Now after all these years, there are many proofs of the sharp hypercontractivity Nelson's theorem in the commutative case, and there aren't so many. In fact, I know of only one for the sharp case for the fermionic thing, and it would be nice if one could look at it from some of these other points of view, some of which have been provided by mass transportation theory. So can one develop this and get a better look at it? And to a good extent, yes, and I'll try to tell you why. Okay, so this is what the equation is, and we want to write this thing. Right. So yeah. Right. So that's our Fokker-Planck equation. Okay. So now let's go ahead and look at the entropy dissipation. And so what we want to do is we want to extract a metric from the entropy dissipation. So the thing to remember in the classical case was if we took the regular classical Fokker-Planck equation and differentiated the relative entropy along the flow, we got something which involved the distance squared, the speed squared along the metric. Okay? Now, if you differentiate this thing, you don't, here's the von Neumann entropy. If you differentiate, of course, when you differentiate the log rho, you just get a 1 over rho d rho by dt, so that gives you nothing. But this guy gives you a rho dot, which is the minus n rho, and so here's what you've got. And then you can integrate by parts, because this is divergence gradient, and this is what you get. And this doesn't look like a square. Now, what happens in the classical case, of course, is you look at this thing, and you write this grad log rho is grad rho over rho, and then you split the rho up and put a square root of rho underneath each one, and then it's gradient of square root of rho with a factor of 4 in it. And what seems to be the good thing to do in this case is to operate on the other guy and to get a logarithm into the game out of this one. Okay? And so here's the thing that comes up. If you take any positive, so this is a factor p, positive density matrices up here, and if you take this ith derivative of this thing, here's a formula for it. And this just involves this product rule, which had the grading operator, which is in it. And it's a very simple thing, because you take, of course, this rho is, the limit is k goes to infinity of this thing with the logarithm. And now you take the gradient of each factor, and this gives you a grad log rho in the middle. And now you let k go off to infinity, and this is what you get. Okay, so that brings that in. Okay, so now you can write this ds by dt, the rate of change of entropy, is this times this. We're making progress now because at least we've got a square of...
That's right. What's the gamma again?
The gamma is the grading operator. So you take the grading operator, so you write out your, whatever the rho is, or any other operator, you write it in this Hermite basis of these monomials of the Q's, and everything that's odd, you put a minus sign in front of it, and everything that's even...
It's just enough parity.
Right, just a parity, right. Mm-hmm. But it, yeah, so it's there and it causes... So that keeps these guys from being the same. Some formulas would be nicer if it weren't there, but there it is. Okay, so now you should think, one would like to think of this as grad log rho squared integrated against rho. See, if the gradient operator weren't here and everything commuted, we'd put these guys together and it would just be grad log squared rho, which is what you get in the classical case. So the analog of multiplying by rho, multiplying c by rho, is this thing. So here's this operation. And we need to divide by rho to work with these formulas, because that's what we're doing it. So how do you do it? So we need to invert this operation. Okay? And this turns out to, okay, so here's this, it turns out to have a simple inverse. So here's this operation. If you have two positive operators, a comma b sharp means you form this gadget. Okay? Now here's the inverse of it, which is just this. Okay? So this transformation has this simple inverse. And indeed, you can see that if a and b were the same and everything commuted, you would just be dividing by a by doing this. And so this is what that is. And this is a very simple, here's the whole proof. You just have to compute the matrix elements. So you pick an orthonormal basis of the a and another one for the b guy. And you compute matrix elements. And then you just need this integral to come out to 1. And it works out to be 1. And so that's that. So here's an operation. This is this inverse gadget of it. And this is kind of, it's a nice thing. So if you take any a and b, so this gadget is not going to be self-adjoint in general by itself, even if these things are not commuting. But if I form c, ab sharp c, this is always positive, this trace, under the trace. Okay? And it's equal to 0 if and only if the c is 0. So these are some simple computations one does with this thing. And this operation is self-adjoint. So if I take the AB sharp and apply it to D and take the Hilbert-Schmidt inner product, that's the same as applying it the other way around, like so. Okay, so good. So now we can write this thing so far like this. So using this machinery, this rate of change of the entropy is like this. Okay, and we've got strict decrease by what we just said. This is strictly decreasing unless this rho is equal to the identity, which is the only case in which this thing is 0. Okay, so now it's more or less clear what a metric is going to be. So I'm going to define an inner product, and I don't know if anything like this has come up before. This is not the way one defines these generalized LP spaces in Hagerup's theory, which has the density matrix put in just with powers and not this more intricate integral way, but here's the inner product. So the inner product of two operators A and B is trace of A star and then this gamma star. So in some sense, you're morally, if everything were commuting, you would just be taking A star B trace against rho. But you're putting rho in this averaged out way. If you were doing this a la Hagerup, for people who worried about the non-commutative LP spaces, you would just be putting a square root of rho and a square root of rho on each side. It's a different thing, okay?
But that is positive.
And that is positive. That was this previous, yeah, that was this. And so you have to do a little bit of chunking to see it, but it does give you its positive and positive definite. That's what that last bit said. And then you define norms like so. And
Can I see that no again?
okay. So if you do it, so here's on the diagonal.
But you're assuming that the A and B are positive, right?
Yes. I'm assuming, but that's going to be the case here because this, what we're doing here is with this,
So it's
this guy. See,
it's
even,
a metric on positive matrices.
well, so the A and the B are these guys,
Yeah.
right? And now even if you started off with something which was rank 1, as soon as you do the flow, it becomes positive. It spreads it out. It's like it's a positivity improving operation. And so these guys will be, even if the rho naught wasn't positive, these guys will be strictly positive. And then this thing says that the only way you've got 0 in here is if the log gradients are 0. Okay? So that's so this is this structure that comes up on here. Okay. So now we can write down this continuity equation. And so if you've got this continuously differentiable curve, here's the rho dot. Okay. This is now something, now we can do it rigorously in this really finite dimensional setting for fixed n. The rho dot has 0 trace because the trace is constant. And so it's not in the null space of n. So rho dot is n inverse like this, but the n is a divergence. So defining A of t to be the gradient, then here's almost a continuity equation. Except now what I have to do is I have to multiply and divide by rho. Okay? And we know how to do that. So I define the V. Whoops. Okay. So I take this A, and I want to get a vector field V in it, which is going to give me a continuity equation. So I know how to multiply and divide. So dividing is this thing. That was our dividing operation. And so if I define V to be this, then I can write the continuity equation in this form. Hat is like the inverse. This operation which shows up here is multiplying. Think about, I mean, what you'd really like to see here is just divergence of rho vector field. So this should be the multiplying of this thing. Okay. Now, if the V is the inverse operation, so the hat divides, then all you really have here is A, because I'm undoing this division, and this was what the A was down here, and so that works out. So you can always write something in this form, and this is what shows up over here.
Well, I still don't understand the answer to your expression. What does the hat mean?
So the hat is this operation. Oh, let me write this operator up. So here it is. So that's this thing. So you take so A and B are given, and this is a transformation on operators, and this is the relevant version of dividing by rho. This is what dividing by rho works out to be, so everything lands on its feet. And the other guy without the hat is this thing which does multiplication by rho. Okay? And so if we multiply and divide by rho, then you can write any path, the derivative of any path in density matrix space like this in terms of some vector field. Okay? And so this is what we'll call the continuity equation. Okay? Now, there are lots of these you can use. This is one particular construction, and let me just tell you, here's the analog of this thing, and it's almost like you just have to dot the i's and cross the t's. It's this projection lemma stuff. The set of all v's that make this true is a closed convex set. There's a unique element of minimal norm. It's got to have some orthogonality to divergences, and therefore it's going to be a gradient. And what you have to sweat, what we had to sweat a little bit about, it's going to be a gradient of some self-adjoint thing. And so this is what comes out at the end of the day, is among all vector fields, the one that minimizes the norm. Well, there's one which minimizes the norm, and it's the gradient of a self-adjoint operator observable on the fermionic space. Okay, so that's this gadget here. And so that's going to be, this is going to be what the tangent space is. The tangent space to, at a density rho, is the set of all gradients of self-adjoint operators in the algebra. Okay, good. And so now we know what the metric is. Okay, and so we take the tangent vector, which is this gradient. You can always write this thing in terms of a gradient of a self-adjoint thing. That's what we just saw. And now here's the Riemannian metric. You take that inner product, which we wrote down before, which is like gradient of u squared against rho, but here's how you multiply against rho, and this defines a metric. Now, this is a bona fide, just plain Riemannian metric on a finite dimensional Riemannian manifold for fixed n. Right? Because this really is a Riemannian metric. It really is a tangent space. And so this just is a plain metric. There's nothing, this is not a quantum metric in some sense that Alain Cohn might talk about. This is really a Riemannian metric.
I just missed the argument by, again, in this formalism, there is a gradient vector field that always makes sense. It doesn't jump. What was the argument?
What? Okay, it's well. Let me pull this. Okay, so when you do this, the set of you can go back to the first page. Let me just do it with the words which are here. I mean, if you look at the set of all v's which make this true, this was a closed convex set. Yeah. Okay. Now, what are the perturbations you can make? I can add to this anything w so that divergence of rho w equals 0. So if you look at the Euler-Lagrange equation that's satisfied by this unique minimal element, it has to be orthogonal to all of those things. Right? And now if you sort out what this means, absorbing it has to be orthogonal in the rho space, and now you absorb it back into just against tau, what that tells you is that the V naught has to be orthogonal to all divergence-free vector fields W. And then that means it's a gradient, just as it would in Euclidean space. Okay? Because clearly the set of variations you can make that keep this condition preserved are things so that rho times that is going to be divergence free. So you have to be orthogonal to those.
Integration by parts.
Exactly. As in the commutative case. And what you have to, there's some sweat, a little sweat so that something has to be self-adjoint, and there's a couple of pages of stuff in the paper. But really you should think of it just as, I mean, you know, the projection theorem gives you a minimizer. It satisfies an Euler-Lagrange equation. The Euler-Lagrange equation clearly tells you that this V naught is orthogonal in some sense to something that's divergence-free. Okay? Well, it's rho times something that's rho times something is divergence-free, but that's orthogonal in L2 of rho. But then you absorb the rho, and the W has to be orthogonal with respect to Lebesgue measure, just as it did in the classical case. And so therefore it's divergence-free. So it's orthogonal. The V naught has to be orthogonal to everything that's divergence-free, and therefore is a gradient. Okay, and then the self-adjoint gets a little messier here for that thing. So now we know what this metric is, and now you can work out what gradients are for this thing. Oh, let me be careful here. Okay, whoops. Okay, great, getting somewhere. So if you take the, right, so let's look at a function like the entropy. So this is a function where we've got some little f of rho, and we're taking the trace of that. So somewhere this thing is written down. Yes, here it is, right? That's at the bottom of the page, of course, right? You take little f of rho and take the trace. So the entropy is such a thing where the little f is x log x. Okay? If you differentiate this, okay, here's what you get. Now the gradient, right, the gradient is the vector field by definition, so that this derivative of the function is the tangent vector inner product with the gradient. That's how you define the gradient. And so you do a simple computation, and it works out to be this. And so this thing is the gradient of that functional. You take the derivative of the little f and take the gradient in the function space of that. Okay? Good. So now we can compute yeah, so here's the gradient flow evolution equation written in this Fokker-Planck equation form, which is equivalent to this. So this is the equation for gradient flow for this functional f. Okay? And if you do this for the entropy, this is what you get. And you do the grad log rho, it's easy to compute that you get this, you take the gradient, and indeed it works out to be exactly what this Fermionic Fokker-Planck equation was. So that Fermionic Fokker-Planck equation is gradient flow for the entropy in this metric. Okay, good. So now I'm going to want to put this thing together. Once you have this thing realized as gradient flow, there are a number of functional inequalities that are directly connected with that, and I can explain. Yes, good, doing fine. I can explain this quickly. So remember, let's just go back through this dissipation. This is what we had at the beginning. If I take the length squared of the tangent vector field, the velocity vector field in the function space, that is what this is. This is exactly just the dissipation of the entropy. This is a consequence of the fact that this time derivative here, well, the dynamical equation is gradient flow for the entropy. Now we know something about how the entropy is decreasing under this equation, because we have a logarithmic Sobolev inequality which tells us how fast that thing dissipates. Okay? And so in fact we know that the entropy is decreasing like e to the minus 2t times what it is. Okay? And this follows from this, this is an easier inequality. This is the sharp logarithmic Sobolev inequality that Elliott and I proved in early 90s. And this is another one which you can get from some Braskamp-Lieb inequalities we proved later. This is all you need here. This is just the rate of change of the entropy that we've been looking at. And there's this inequality, which is weaker than that one and a little easier to prove. But this tells you that this decays like e to the minus 2t. Okay? Now, that gives you a Talagrand type inequality. And a Talagrand inequality relates this relative entropy to the distance in the Wasserstein metric. So exactly what the Talagrand inequality says. It has the relative entropy. Remember, this is relative entropy with respect to the reference state, okay? And dominating the Wasserstein distance to the Gaussian measure. So exactly that inequality, that with this constant, appropriate constant, which is again the same 2 in here, that the relative entropy dominates the square of the Wasserstein distance, is the Talagrand inequality. Okay? So how does this come out from this framework? Well, this is kind of cute. So, and something like this happens in great general. So you write down this distance from the identity. We're using the fact that as t goes to infinity, the rho of t converges to the identity. So this distance is the arc length along the solution of the Fokker-Planck equation. That's just what it is. Okay? Because this is some path which does it. Okay? So and you compute this. Now, since this thing without the square root is the rate of change of the entropy, by the Schwarz inequality you get the square root of t2 minus t1 times the square root of the entropy increment. And now define a sequence of times, and these times are the times it takes at which the entropy goes down by a factor of e to the minus k epsilon. So this is the kth time. So every time it goes down another e to the minus epsilon, you've got the next time increment on here. Okay? So by the dissipation bound, we know how fast this thing is decaying, which is this result here. You have a bound on how long you have to wait, so these things are less than epsilon over 2. And so therefore, with this choice being put in, you have, this is the square root of t1 minus t2, and this is the difference in the entropies. And so you've got this, and we have to sum these guys up. But now notice what this is going to be. This is effectively another epsilon, so it's like a square root of epsilon, just as like an epsilon times this thing, which is essentially an integral. So it's all written out here. I mean, if you sum this thing up and let the epsilon go to 0, you're just integrating this up, and you get 2, and that's the bound. So this is something that always happens when you have a gradient flow equation for some metric. Whatever that distance is, the distance to the equilibrium point is always controlled by the distance from where you start. And if you think about it, what this is suggesting is a convexity result, because if the entropy function is convex, bounded below, the Hessian is bounded below, then as you go out from the equilibrium to some point, you've got to go up at least as much as if you were going up with this quadratic bound if the Hessian is bounded below. And this is what this would give you. So this is suggestive of the fact that this entropy should be convex, which it is in the classical case. Okay? So this is what we thought we would like to be able to prove next. And so everything fits together. We have a sharp Talagrand inequality, which is the exact analog of the one for the Gaussian case. And so the next result, the thing that's true in the classical case, is that the entropy function, the relative entropy with respect to the Gaussian, is strictly convex. The Hessian is bounded below by 1. Okay? So question, is that true in this case? Now, what do we mean by the Hessian? We have to say what the geodesics are, because when you compute the Hessian in a given direction, you take a geodesic with a certain direction, and you differentiate twice along that geodesic in that direction, and that gives you the Hessian applied to that thing. So can one prove that? And not completely yet. So let me tell you what this. This does give you an interesting thing. It tells you, by the way, that the right. I mean, the thing which has the highest relative entropy. Elliot would be furious with my sign change here, calling this S. I guess I should have H, because it's relative entropy, not the entropy it's supposed to be concave. The highest version of this, though, is this n over 2 log 2, and so. Right. Mm-hmm. And so this is the diameter of this. So indeed, this is the diameter of the space. So the more fermionic degrees of freedom you have, the higher the entropy can get, like this n over 2. And that gives you a control of the diameter of the space, because this quantity here controls the distance to the identity. And so that gives you a bound on the diameter. And okay, so that's one thing that comes out of this gadget. Now, I'm going to say this is sort of an awful, there's another really awful formula which comes up in here. So there's this rho flat thing. And so here's what it is. The thing to notice, though, is that if everything commuted, it would just be v1 dot v2. So there are rows going in and out and so forth, and they'd just be v1 and v2. So if you take this variational formula for the distance and you work out what the Euler-Lagrange equations for it are, well, let me tell you what you get classically. If you did the same kind of thing from this I showed you from Brenier and Benamou, we had this variational principle for the action. If you write down what the Euler-Lagrange equations are, you get this Hamilton-Jacobi system. Right? That's what just comes out. So the geodesics are characterized. In other words, if you want to know how this U, which is the potential, is changing as you move along a geodesic, the answer is given by the Hamilton-Jacobi equation. So if you start out with U and you want to know how U changes, so you can take a second derivative, which is what you need to do to compute a Hessian, you need to be able to differentiate the tangent vector. Well, this is how you do it. Now, this thing has this strange, this is the continuity equation. That's the continuity equation. This is the Hamilton-Jacobi equation. Okay? And there's this funny rho dependence in here, but again, if everything commuted, they would drop out, but there they are, and it makes this a little harder to work with. So this is it. So we're getting right down to the end. Good, just in time. So if you take the thing, this is the next thing we tried to prove. And with much effort, we have proved. So that's funny. Oh, we would have loved to have proved this. I don't know what got typed out there. It's the end of the slide. We would have loved to have proved that this was true for all n. This is the statement that the Hessian is the bottom eigenvalue of the Hessian is bounded below by 1. If you knew that, you'd have enough convexity to prove the logarithmic Sobolev inequality, hypercontractivity, and everything would follow from the geometric properties, just as it does in this case. And one might be able then to adapt this to other metrics, other functionals, and get other. I mean, there's a shortage of situations in which one can prove hypercontractive estimates in these systems. So we were hoping to get a second way of proving this. So far we don't. I mean, the computation for n equals 2 is rather tricky. But all of the evidence suggests that there is. I mean, this inequality would give you, it's sort of the signature, the logarithmic Sobolev inequality that we do have is sort of the signature of this. The curious thing is that in the classical commutative setting, it's easier to prove the convexity. You just differentiate along the Hamilton-Jacobi equations. You prove the convexity. And then the logarithmic Sobolev inequality and hypercontractivity is an easy consequence, is the way one might look at it now. Unfortunately, the Hamilton-Jacobi equation, which characterizes the geodesics, is a little complicated. And at this stage, we don't know how to prove this thing in general. But it would be interesting if anyone came up with any good idea, and we're still looking at it. But this is the conjecture we put, is that this should be true, and then everything would fit together with the analogy between the classical case and the quantum case, and one would have another way of looking at how the hypercontractivity for this Fermionic Fokker-Planck equation arises through convexity of the entropy. Okay, but at this stage, the story is incomplete at this point, and so that's the last slide, and that's the end of the talk.